Hi, I'm Baek, and today I'll be talking about BASECOMP, a comparative analysis for integrity protection in cellular baseband software. This is a work done with Insu Kim, CheolJun Park, Dongkwan Kim, together with professors Yongdae Kim and Insu. So recent smartphones have multiple processors. The application processor runs the operating system, as well as all the applications like the ones you see here. On the other hand, the baseband processor runs a real-time software that handles actual cellular communication. The attack scenario we consider here is a malicious base station controlling the communication data with a vulnerability in the real-time software. The baseband handles control plane protocols. In particular, layer 3 includes core procedures such as call control, mobility management, and session management. This is a brief overview of how the processor handles layer 3 protocol messages. Messages are sent through the security checker, message decoder, and then the message dispatcher, which sends each message to its corresponding handler. What we aim to do here is to find vulnerabilities in the security checker. But there are several challenges when trying to analyze baseband software. The first one is, as the vendors do not release implementation details, the obscurity hinders the readability. Second, because baseband softwares have to implement specification documents of hundreds of pages, the binary size is extremely large. Now, there were previous approaches that tried to tackle this. A majority of them, including Doltest and firmware, use dynamic analysis, which sends messages and observes responses from real or emulated devices. However, as not all messages can be tested, the search space had to be reduced, which eventually led to missing bugs. And there was also a static approach proposed in BaseSpec. However, this could only be used on message decoding and could not be applied to integrity protection. In addition, it also relied a lot on manual analysis. So we propose a new static approach combining comparative analysis and probabilistic inference. With comparative analysis, we compare the implemented integrity protection logics with the specification. And to reduce the amount of manual effort needed, we use probabilistic inference to find the integrity protection function automatically. So this is an overview of our system, BASECOMP. With the firmware as the input, BASECOMP first finds the integrity protection function through probabilistic inference. Then, with a little aid of manual analysis, BASECOMP does symbolic execution to collect constraints and creates an implementation model. Then, with the reference model created from the specification, BASECOMP compares the two models and results with mismatches. So the first step is to find the integrity protection function with probabilistic inference. This step is based on the assumption that the integrity protection function we find needs to have the two logics. First, it has to do encryption and decryption for calculating the MAC. And second, it has to have message type filtering logic based on a subclass in the specification. With these, BASECOMP follows the three steps to find the integrity protection function. The first step is to find the MAC function, which should have routines using ZUC and Snow3G as the encryption algorithm. We find the cryptographic functions by finding functions referencing the S boxes of each algorithm. Then we prioritize common ancestors of these two, which would be both functions 1 and function 2 in this given call graph. Next, based on the assumption that the function we find would be closer to the cryptographic functions, we then prioritize lower common ancestors, so that in this case, function 1 has a higher probability than function 2 to be the MAC function we find. Then the second step is identifying the message type comparing function. The subclass 4.4.4.2 in TS 24.301 specifies the message types that can be accepted by the baseband before a secure communication channel is established. By using the values here, we find the variable that should contain the message type. Now, BASECOMP iterates every function and variable in the software and collects comparisons with constants. Then by comparing the constants with the ones specified in the subclass, it either higher or lowers the probability of the variable to be the one holding the message type. Then the probability of the function to be the message type comparing function follows the variable with the highest value. So in this case, function 1's probability would be the probability of variable 1. Then the final step would be using the same method used in the first step to find the integrity protection function that should call both the MAC function and the message type comparing function. The next step is gathering additional information about the firmware before BASECOMP does symbolic execution. First, BASECOMP requires a vendor-specific analysis module, which includes logics that differ by vendor, such as how to symbolize the variables or how to decide if a message is accepted. The symbolize function in the red box specifies that the message buffer is stored in the R0 register and the security state in an address specified by the user, which should be given through a configuration file. And the function accepting in this box specifies that a message is considered accepted if the return value of the integrity protection function is 1. And in addition to the previous vendor-specific analysis module, BASECOMP also requires a firmware-specific configuration file per firmware, including information used by the vendor-specific module, addresses of functions and where interesting values are stored, and a list of functions to skip while doing symbolic execution for preventing path explosion are stored in this file. With these provided from the analyzer, BASECOMP then does symbolic analysis. So BASECOMP does under-constraint symbolic execution on the integrity protection function and collects constraints related to the message buffer. For a brief explanation of how this works, the code on the right is a simplified version of the integrity protection function and its callees. For the message given as the function argument to be treated valid, the conditions in the if statement inside the white box has to be true. So when taking a look into the called check header function, it first parses the security header type and message type from the message. Then if the security state is secure, the function returns true if the security header is not 0 and smaller or equal to 3. And if the security state is not secure, the security header type has to be 0, and the message type has to be one of the values in the cases here to return true. Then with the other verification functions also returning true, the message would be considered accepted. Now BASECOMP collects these kind of constraints and creates an implementation model. Finally, the last step would be comparing the created implementation model with the reference model created from the specification to get mismatches. To evaluate our system, we answered the 2 questions. First, how well can BASECOMP find the integrity protection function? And second, how effectively can BASECOMP discover bugs? For the dataset, we used a total of 16 images from 3 vendors, where 2 are from the top 3 mobile processors. And in addition, the image used the architectures ARM MIPS with an extension and x86. So for the first question, we checked the rank of the genuine integrity protection function of the 16 images. As you can see, most of them were ranked first, and the average rank as 1.56 out of an average of 82,000 functions per image, proving that it is effective in finding the integrity protection function automatically. Second, BASECOMP reported 34 mismatches from the 16 images, and 29 of them were confirmed as true positives through on-the-air testing. 5 were false positives, mostly caused by security checks implemented outside of our analysis scope. Now, to take a deeper look into one of the bugs BASECOMP found, I'll first briefly explain the NAS authentication and key agreement process. For user equipment and a base station to establish a secure communication channel, the 2 have to exchange a sequence of messages such as authentication request, response, and security mode command and complete. Now, bypassing this AKA process means that an attacker can freely attach to the victim without exchanging these kind of sequence of messages and can just send arbitrary NAS messages in plain text. This would let the attacker gather the victim's information or even modify them on their device. BASECOMP found this NAS AKA bypass vulnerability in Samsung Baseband, which is caused by a logical error. This code here is a simplified version of the integrity protection function where this bug was found. Looking into the integrity protection function, the check header function, check sequence function, and validate MAC function must return true for the message to be treated valid. The first violation of specification is that the check header function returns true in the insecure state if the security header is not 0. And in addition, the other validating functions only check the messages when the security header type is between 1 and 3. So if the security header is larger than 3, the message is accepted regardless of any other element of the message. Other approaches analyzing the baseband software fail to find this bug, as the security header larger than 3 is considered semantically invalid. Now, this is a demo video of an attacker sending an arbitrary SMS message using the bug. As you can see, the sender, time, and data can be modified by the attacker as wanted, obviously making attacks like phishing easy afterwards. In conclusion, we proposed a novel semi-automatic approach using probabilistic inference and comparative analysis to analyze the integrity protection in baseband software. And we could find a total of 29 bugs from 3 vendors, including a critical NAS AKA bypass vulnerability. Thank you. That's the end of my presentation, and feel free to ask any questions. Okay.